we have found our optimal number of boats in the equilibrium, which is B star O. So let's go ahead as before and find out the other quantities we want, like the equilibrium stock and the harvesting. So what is the fish stock? So let's go ahead and write it this way. So let's write it S star O, which is simply going to be our function of the stock as function of the equilibrium number of boats, B star O. And this, you may remember that it was equal to K times 1 minus B star alpha divided by R. But then what we can do is already say that this is B star O here, right? And now what we can do is substitute the optimal number of boats, which is this expression there that we just found in the previous video. R over 2 alpha multiplying 1 minus C divided by P alpha K. So let's just go ahead and simplify this expression. So alpha over R simplifies with R over alpha, so it disappears. And then minus 1/2 by 1 minus 1/2 by minus C over P alpha K, where I'm going to get the following. And then, so obviously, this is going to simplify. 1 minus 1/2 is 1/2. So I can have the 1/2 in front here. And then let's go ahead and put the K inside it. And here K divided by K is going to disappear. And in fact, let's just have these two things at the numerator, and we get this expression here. So what do we find? Well, contrary to the previous stock, if you remember, the previous stock was simply C divided by P alpha and was purely a function of the industry and the catching efficiency alpha. So the boats really didn't care all that much about the stock or anything. Now at least it looks like the equilibrium stock is going to be determined at least in part by K, the carrying capacity. And so we can even just go ahead and substitute what we had before, C divided by P alpha, which was the S star F, so the stock of fish in the free fishing case. And so what do we see? Well, we see obviously that the free fishing was lower than what's going to be the optimal fishing, because the optimal fishing is going to be basically an average between the total carrying capacity K and the free fishing. So again, it's going to at least in part be dictated by K, whereas free fishing was just dictated by the price and the cost. Okay, now let's go ahead and so that's what I'm writing here. Optimal fishing uses only half the boats used when there was free fishing, so S star O is closer to carrying capacity. Now let's go ahead and compute total harvest. Total harvest is going to be H star O. And this is, as we remember, the fishing efficiency that multiplies the number of boats that multiplies the stock of fish. So let's just go ahead and substitute all these values. So for the optimal stock of boat, quantity of boat, we have this, and for the optimal stock of fish, we have that. Now it's just a whole fun doing algebra. So first, let's go ahead and put this 4. So just multiply by 1/2 here. So we can divide by 1/2 here. And then let's just multiply this inside the parentheses. So we get this expression. Now, so I can multiply this by what's inside the parentheses and get this expression there. K over K can simplify. C over P alpha minus C over P alpha is 0. Here I have a minus. And why don't we go ahead and multiply by K in front and divide by K inside? So we get 1, and then we have K here. And as you can see, we have basically a difference of squared. So let's just keep it as a difference of squares. And here alpha will cancel with alpha at the denominator. So this is just squared. All right, so that was a whole lot of fun. I encourage you to do it on your own to make sure you understand what's going on. So what can we say about this? Well, actually, we can't definitely compare it to the stock of the free fishing. Well, we could, but it's a bit complicated. So let's not do it. But let's just appreciate the fact that, well, first of all, notice that P alpha K is larger than C by assumption, because we want the fishing activity to be profitable if there's only one or slight fraction of one boat in the sea. So P alpha K has to be larger than C. So this is positive. And then yes, so if the carrying capacity increases, then total harvest increase. If the reproduction rate increases, then total harvests are larger, of course, because fishes reproduce faster, so we can harvest more of them. And yes, if the cost per boat increases, then total harvest decrease. If the price of fishes increases, then it's more profitable to harvest. So yeah, P and C are always together because they represent prices, basically. So that's what we find. So now let's go ahead and look at what this looks like on our dynamics graph. So imagine that the free fishing was this red line here. Then we found out that actually the intensity of fishing in the optimal fishing will be essentially divided by 2. Because we have that the number of boats in the ocean are actually 1/2 what they were in the free fishing case. So obviously the stock of fish in the optimal fishing industry is going to be larger than the stock of fish in the free fishing industry. So question is the harvest going to be larger or smaller in the optimal fishing industry compared to the free fishing? Well, here you can just see it when with your own eyes that the harvest was actually larger. However, that doesn't mean that it's optimal. What we want is to maximize the profit of the fishing industry. And here we have essentially too many boats, so we pay too much for the captures, the extra captures that we have. But note that if we were, say, with optimal fishing around here, then it's possible that the free fishing would be around here, and then that in that case actually the harvest would be even larger in the optimal fishing case than in the free fishing case. So that if that was the case, really that's really a depressing situation. If the industry is not regulated, it means that, well, it looks basically like what say the cod or the bluefin tuna industry look today, where everybody is fighting over a very small number of fishes. compared to what they could achieve if they were able to cooperate with each other and achieve a state where they actually have to spend less because they just need to put fewer fishing boats in the sea, and they are able to catch more fishes and make better profits. So speaking of profit, we can go ahead and quickly compute them. So total profits are going to be profits of B star O, which are essentially so the number of boats that multiplies the profit of one boat, which was, if you remember, a function of the optimal of the stock of fish. So now it's the function of the optimal stock of fish. So yeah, to be completely correct, I should have written S of B star O, but we already know it's S star O. Let's substitute the individual profit for one boat. So we get equals to, yeah, let's go here, B star O, and then the individual profit was sales price multiplied by fishing efficiency, that multiplies the total stock of fish in the ocean, star O, minus cost. And then let's finish by substituting the optimal number of boats, B star O, and the optimal stock, S star O. And now we can have a whole lot of fun simplifying this expression. So I suggest doing the following. So let's divide C by P alpha K here. And then let's divide this by P alpha K, and let's multiply the whole expression by P alpha K. We haven't changed anything. And now we can use that to simplify a lot. So P alpha is going to disappear. Then K I can divide by K here, and then K there. So here I can multiply this by 2 and divide by 2. And actually what I can do then is put it here. So what do I get? Well, let's just have another line. C divided by Kp alpha minus 2C divided by Pk alpha gives me minus C divided by Pk alpha. And so the 1/2, let's multiply it at the beginning. So I get 1/4. And this is just the same as this expression here. So I can just put a square. And alpha is the same as alpha, I simplify it. So this is my final expression for the profit. Rp alpha divided by 4, that multiplies 1 minus C divided by P alpha K squared. So what is the interpretation of this profit function? Well, it has intuitive interpretation. So when the sales price goes up, so P goes up here, and minus and P is at the denominator. So this goes up, but this whole expression goes up. And why am I sure? Well, because again, P alpha K is larger than C, so C over P alpha K is smaller than 1. If the cost of renting a boat goes up, then the profit goes down. If the reproduction rate of fishes goes up, then it's good for profits. So yeah, everything makes sense. Now just to test you, so how does that compare to free fishing profits? Well, it's bigger because free fishing profits are by definition equal to 0. So for now, all we have done is look at what happens in steady states. So with stars here. So we haven't talked about transition. We're not going to do it because it would require much more additional assumption about the model, so we don't have to do that for now. But yeah, so now we can go ahead and ask some policy questions related to this.